Hi there, today we're going to be looking at quadratic equations and quadratic functions and some connections between the two. There's a lot that one can tell us about the other, but of course if they're quadratic then they of course contain some kind of quadratic expression, right? Something that usually can be arranged in the pattern of ax squared plus bx plus c, that's a quadratic expression. We're going to look at the quadratic equation x squared minus x minus 6 equals 0 and the similar quadratic function y equals x squared minus x minus 6. Both of these contain the same quadratic expression, x squared minus x minus 6. What might we be asked to do with these? Well, if it's an equation, most often we'll be asked to solve it, right? And find what x can be to make it true. We'll find the solutions, or the roots. With the function, what might we be asked to do? Well, a few things. We might be asked to find some coordinates that make it true, right? We would need a value for x to be paired with a value for y. One thing that we'll often be asked to do, especially in upcoming units, would be to graph this function. And in fact, I happen to have asked Desmos to graph this for me. So here I have a graph of the function y equals x squared minus x minus 6. There it is. Let's just take a look back at our equation. And let's say we are going to solve it. How can we solve it? Well, we've solved by factoring before. Solve by factoring. Good thing we've practiced so much quadratic factoring. That factors to x minus 3 and x plus 2. And that equals 0, and I'll break that into two equations. X plus 2 equals 0, so x must equal 3, and x must equal negative 2. Now, you've been introduced before to the idea that the solutions to your quadratic equation correspond to the x-intercepts of the graph of your function. So you'll notice that there is an x-intercept here at negative 2, 0. There's another one here at 3, 0. So the x-intercepts, right, also sometimes called the zeros of the graph, correspond directly to the solutions of the similar quadratic equation. Okay, so here again we see that same graph we saw before. This is the graph of the function, the quadratic function x squared minus x minus 6 equals y. And it's pretty representative of a lot of the graphs of quadratic functions. What is going to be true about all quadratic functions? Well, they're all going to have this kind of rounded U-y shape. We have a name for it. It's called a parabola. Right, a parabolic shape. So parabolas can be pretty wide. They can be pretty skinny. Oh, that's a pretty ugly one. They can open up, right? They can kind of get wider at the top. They can get wider at the bottom. They can open down. But they all have this parabolic shape to them. What else do all graphs of quadratic functions have? Well, this one, right, has x-intercepts. And this one has 2. Now, I'm just going to make this point that, well, what if we drew a parabola that did something like this? It would still be a parabola, and they do exist up here. So here's an example of a parabola. It's still a graph of a quadratic function, but it has 0 intercepts. And perhaps you could imagine there's a such thing as a parabola that just comes down and exactly touches the x-intercept in one place only. And so it is true that a quadratic function, the graph, can have 2, 1, or 0 x-intercepts, depending on which specific quadratic function we're talking about. You may notice as well that a parabola is symmetrical, right? It's even to the left and the right. And if we were to actually kind of draw the line of symmetry on the parabola that we have here, I think it would go somewhere down the middle here. Right? So there is a line of symmetry. Now, it's going to be a line straight down the middle, and one important part of where the line of symmetry is going to be is, well, it's going to actually be exactly halfway between the x-intercepts. So if I know exactly where the x-intercepts, I can actually draw a line halfway between them, and that would be the line of symmetry of my parabola. Well, in this particular case, where would it be? Well, I know I have x-intercepts at -2 and at 3, right? And how do I find what's exactly halfway? I find the average, add them together, -2 plus 3, divide by 2, and I think I get 1/2. So I know that this line is going through 1/2, and since it's a vertical line, I know that the equation of my axis of symmetry is the equation x equals 1/2, right? Remember, vertical lines just have that special equation, x equals whatever number it goes through. So line of symmetry at x equals 1/2 in this case. The last thing that we always find on a parabola is this point, right? It comes at where it stops going down and starts going up. All right, and if it's upside down, I guess it would be the point where it stops going up and the point where it starts coming down. This point right here, where the shape reaches some kind of minimum value. Notice that the shape doesn't go anywhere lower than this. So this spot right here, we give a name. We call this the vertex. So every graph of a quadratic function, every parabola has a vertex. And the vertex is a coordinate. Right? It happens at this one spot. Now, this particular vertex that we're looking at, we know half of the coordinate. We know that the vertex, it must happen on the axis of symmetry. So we know that the first half of our coordinate for our vertex is 1/2. And then the question becomes, well, what's the other half of that vertex? Looks like it's somewhere south of -6. How can we know for sure? Well, if we know, and we do, if we know the quadratic function, then all we have to do, right, if we know an x value, all we have to do is sub it into that quadratic function and solve for y. So we're going to sub x equals 1/2 into y equals x squared minus x minus 6. So away we go. Y equals 1/2 squared minus 1/2 minus 6. 1/2 squared is 1/4 minus 1/2 minus 6. Well, 1/4 minus 1/2 is -1/4, and a -1/4 minus 6 then works out to, of course, -6 1/4. Right? That's one way to put it. So we know that our vertex coordinate there is 1/2 -6 1/4. So, for your work in class and for homework, you might be given an example like this that I've taken from page 289, where you are given a quadratic function like y equals x squared plus 9x plus 14, and you are asked to find the x-intercepts, to find the vertex, and then to graph the function. Well, if we are ever going to find x-intercepts, I would expect you to communicate that you are going to let y equals 0. That's how you find an x-intercept. You let y equals 0. If you need to find a y-intercept, then you would let x equals 0. So we're going to let y equals 0, and we're going to say, well, that means that 0 equals x squared plus 9x plus 14. And thus far in, you know how to solve this by factoring, so we are going to factor this part down. Two numbers that multiply to 14 and add to 9 must be x plus 7, and x plus 2 still equals 0. And therefore, x must equal -7, and x must equal -2. Okay, so therefore, my x-intercepts are at -7, 0, and at -2, 0. Because I'm going to be graphing this thing, I probably want to keep track of all the points that I know are on this graph. So far in this little table of i's, I'm keeping track that I know the points -7, 0, and -2, 0. All right, well, in order to find the vertex, I probably want to find the axis of symmetry, right? So the axis of symmetry happens at the average of the x-intercepts. So x equals -7 plus -2 divided by 2, and that equals -9/2. So the axis of symmetry at x equals -9/2. So that means if I want to find the vertex, I know that the x value of the vertex is going to be at -9/2. To find the corresponding y value, I'm going to sub x equals -9/2 into the equation, or the function equation. So y equals inside the brackets, 9/2 squared plus 9 times -9/2 plus 14. And that's 81/4 plus, minus 81/2 plus 14. If I were to do this all with common denominators, then I would say that this was 81/4 minus, 162/4 plus 56/4. And my calculator says that it is -25/4. So I know that this is there. And so now if I wanted, by the way, to put those in coordinates into, mixed fractions so that they're easy to read, well, that's -4.5, and this is -6.25. So if I wanted to graph this, I would move some of my stuff out of the way here, and that one as well, and drop in a quick, there we go. I'm still running. All right, I'm gonna move this out of the way. Oops. Good. All right, so I know I have got some x-intercepts here at -7 and -2. I'll put those on, -7, 0, and this one at -2, 0. I know I've got a vertex that I found here at -4.5, -6.25, -4.5, -6.25, right around here, right? That's -9/2. -16, 25/4, and so all that's left to do is to draw in a nice parabolic shape. Once you've drawn about 1 million of these, you get pretty good. You get the hang of getting the curve nice and even. And there you go. That's what I would expect. A reasonable parabolic shape that for sure goes through the vertex. Often I label that with a V. Through your two x-intercepts. And that's how it's done.